Welcome friends. So we are discussing network theory. This part we shall continue our discussion with some more problems on Norton's theorem. So what is Norton's theorem? First, in order to solve current flowing through any branch, we need to remove the load resistance by short circuiting it, and to measure short circuit current through that short circuited path, which is called Norton's current. Then we should measure Thevenin resistance, and after having doing so, we must construct Norton's equivalent circuit, which is Norton current in parallel with Thevenin resistance and in parallel with load resistance. And then we can evaluate the equivalent current flowing through the R3 using current division rule. So let us proceed towards Norton's equivalent circuit. So let us consider figure 7. We have here find the Norton. So in this problem it is asked to find out Norton's equivalent circuit. So two parameters you need to evaluate. First one is IN and therefore second one is RTH. So let us first across the terminal, of course, X and Y. Okay, across the terminal X and Y. Slide, right. So let us first solve this problem. Short the terminal X and Y, right? Short the terminal X and Y in this way. Now let us, the current flowing through the short circuit terminal is IN, which is Norton equivalent current in this direction from Y to X. And now basically you see this is a new kind of circuit, because you see there are two sides. If you say this is a primary side and this is a secondary side, we have almost separated, two sides are separated with a ground reference. So however, the primary and secondary networks are coupled each other by this factor. So the current flowing through the primary side is I, and that I is determining the magnitude of the dependent source current which is at secondary network. So in this way these two networks are coupled. So from this primary side we can directly write what is the value of I. I is nothing but 4 by 240, which is 1 by 60 ampere. And due to this fact you can straight away analyze that that current dependent current source is nothing but 6 into I, which is 6 into 1 by 60, that is equal to 1 by 10 ampere. That is the dependent source current. And if you analyze the secondary part, you can understand that this 24 ohm resistance is effectively out by this short circuiting. You see this is totally short circuited. So this dependent source, the entire amount of this dependent source current is flowing through this short circuited path, which is IN. So basically IN is nothing but is equal to 1 by 10 ampere, which is equal to 0.1 ampere. So we solve IN is equal to 0.1 ampere. This is the Norton current. Now let us proceed to our next problem. Now as it encounters, okay, one more thing I forget to mention, there is another voltage source attached, or there is another voltage source available in the primary side. Now what is the role of this voltage source in determining the Norton current? You see I have just marked this one as a short circuit. Why? The because is, you see this this dependent source Vxy is dependent on the voltage appearing across X and Y. As long as it is open circuited, it will have some value, but the moment it is shorted, then Vxy becomes 0. Vxy becomes 0, that is why this voltage source removes, or this voltage source disappears. That is why to remove this voltage source, we remove this by short circuiting its individual terminals. Right, that is why this voltage source does not make any impact in determining Norton's current. Now to proceed our discussion, to continue our discussion, since it encounters two dependent sources, we must connect a battery of known voltage, which is EDC, that will inject a current IDC, that is injecting a current IDC in this direction. Now the dependent source voltage becomes EDC, dependent source voltage becomes EDC, and this voltage source, which is independent one, that is removed by short circuiting its terminal. This current was I just considered in the reverse direction, so the direction of the dependent current reverses. The direction of the dependent current source reverses as compared to figure 7, which is mother figure. In the mother figure, the direction of the current from top to bottom, but in the figure 7b, it is shown from bottom to top because this current direction is reversed. So now let us analyze one by one. You see, this EDC, that battery voltage, is directly falling on the 24 volt. Uh, 24 volt resistance, right? And also this EDC, you see, this is the primary side. So if you analyze it, so you can write directly KVL equation as EDC is equal to 240I. This is first. EDC is equal to 240I. From the primary side, we have a dependent source and we have a 240 ohm resistance. The current flowing through it is I. So a drop will be 240I. So they must be counterbalance each other. So EDC must be equal to 240I. Now, if you consider this node X, you see these two currents are entering to this node. One current is IDC. So let me draw this part again. So this 6I current, and therefore we have 24 ohm resistor, and then we have a DC voltage source EDC, and we have a current IDC. So with respect to this node X, IDC is entering, 6I is also entering, but this is leaving. So node at KCL, you see two currents are entering, we must write IDC plus 6I, they are entering as mentioned here, and this current is leaving, which is equal to EDC by 24. Why this current is EDC by 24? Because this battery voltage directly falling across the terminal X and Y. This battery voltage EDC is directly falling on the 24 ohm resistance. So current flowing through this 24 ohm resistance is nothing but EDC by 24. So from equation 10 and 11, if you solve, you can directly write IDC is equal to EDC by 24 minus EDC by 40. If you solve, you will get it by this equation. IDC is equal to EDC by 60. So by removing or by calculating RTH is equal to EDC by IDC, one should get 60 ohm. So this is the Norton's equivalent circuit. we have this is as Norton current, which is 0.1 ampere, and this is RTH, which is Thevenin equivalent resistance as 60 ohm. So this is called Norton's equivalent circuit. Now let us proceed to our next problem, figure number 8. Again, this problem with dependent source. Find the current flowing through the 5 ohm resistance, that is I, right? This is I. So it is 5 ohm resistor. We need to find out this current. So let me solve one by one, or let me analyze this circuit. So let me first remove 5 ohm resistor by short circuiting its terminal, and let us say we will calculate the short circuit current as IN. So let us solve one by one. Now we have a dependent voltage source, that magnitude is 4I0, and its value dependent on this current, that is I0 flowing through the 2 ohm resistor. So by short circuiting it, the 5 ohm resistance, the current magnitude will differ, but however still we consider the same notation, which is I0. This voltage is also 4I0. So we just analyze this circuit. Node Y is the ground node. So if you consider this is a dead short circuit, so the X node will also become the ground node. The potential of X is also the potential at 0 volt. Okay. So according to figure 8, so we write the KVL equation first. So this is 12 volt and this is 2I naught. It is actually, this is the 2I naught current is flowing. Now with respect to this X, so the current flowing through 4 ohm resistance is IN minus I0. Okay. So we have this 2 ohm resistor. This current is I0. We have this short circuited path. This current is IN. And we have this 4 ohm resistor. We consider this current flowing, some current is flowing. So with respect to node X, two currents are entering. One current is I0 and another current, let us say IX, and one current is leaving IN. So with that we can write I0 plus IX is equal to IN. So from there we can directly write Ix is equal to IN minus I0. So that is it. That is why it is written. So now this polarity of this 12 volt and polarity of the 4 ohm resistor, the potential drop across 4 ohm resistor, they are additive. So that is why they are added. 12 plus 4 into this Ix current, which is IN minus I0. And with this, the potential drop across 2 ohm resistance and this dependent voltage source, these two potentials are additive. However, they are subtractive to these two. I naught, that is the drop across 2 ohm resistance, and 4I naught is the dependent source. So if you solve this, we will get an equation of 10I naught minus 4IN is equal to 12, which is equation 12. Now as we are mentioning that this Y node is at ground potential, and due to the short circuiting, the X node also becomes the ground node. So basically the node X is 0 volt. So this I naught is nothing but 12 minus 0 by 2. So I naught is nothing but 12 minus 0 by 2, which is 6 ampere. Is 6 ampere. So from equation 2, one can easily solve IN is equal to 12 ampere. So IN is equal to, if you solve, I0 is equal to 6 ampere. If you substitute, then one can easily solve IN is equal to 60 minus 12, that is 48. 48 by 4, that is equal to 12 ampere. So IN we have evaluated as 12 ampere. Now next process, let us consider the next part, which is Thevenin equivalent resistance. So we remove this voltage source. We remove this voltage source by short circuiting its terminal. We connect a battery of magnitude EDC, which is injecting a current IDC. Now let us consider the currents as shown. So from the figure 8b, if you consider this part, 4 ohm, this is EDC, and this is the dependent source. Let us say EDC, a current IDC. This voltage is actually 4I naught, and there is a one resistance 2 ohm, which is the current flowing through it is I0. So the current flowing through 4 ohm resistance is nothing but I naught plus IDC. So if you apply KVL on this part, the polarity must be something like this. Battery polarity should be like this, plus minus. 4 ohm is like this, plus minus, and here it is already indicated in the problem. So 4 into I naught plus IDC is, and 4 I naught, these two are additive. With respect to that, EDC is subtractive. So this is the KVL equation from the figure 8b. So if you solve, you can get solution or a equation. EDC is equal to 4 IDC plus 8 I0. Now also, if you consider this side, this is short circuited part. So here it is actually plus minus, they are additive in nature, so that is why it is written EDC plus 2I0 is equal to 0. They are additive, so simply they must be added, and according to KVL, net potential of any mesh is equal to 0, so that is why it is written EDC plus 2IDC, 2I naught, because the current flowing is I naught through the 2 ohm resistor here. So it is 2I naught, that will be equal to 0. So from there, I naught is equal to minus EDC by 2. So if you solve equation 13, this one, so you can get, and if you solve this, you will get EDC by IDC, which is equal to RTH is equal to 4 by 5 ohm. So we solve RTH is equal to 4 by 5 ohm. Now our last step is to construct Norton equivalent circuit, that is IN here in parallel to RTH and RL. Now the current flowing through the RL is find out by this formula. Norton current is 12, and the formula will be resistance of the other branch, that means RTH is equal to 4 by 5. Now 4 by 5 plus load resistance is equal to 5 ohm. So if you solve this, you will get the current flowing through is 48 by 29 ampere. This is the Norton's theorem. So the current flowing through the 5 ohm resistance is 48 by 29 ampere. So first we have solved IN by short circuiting the load. Then we have followed the standard procedure to measure RTH by connecting a DC voltage source or battery. And finally, once we have solved IN and RTH, then we can construct the Norton's equivalent circuit to calculate the current flowing through the load resistance. This is the problem. These two problems we solved using Norton's theorem. There, the Thevenin resistance calculation part is exactly same as you compared with the Thevenin theorem and Norton's theorem. They are same, but the difference is to calculate the Norton current, and with the incorporation of dependent source, the problem will become little difficult, or I would say little complex. So one should have the prior practice in order to know in order to have the inner gripping of the or the inner ability to solve the problem efficiently. Okay, so with this, let us end this part here. In the next part, we shall discuss some more problems with mesh analysis and nodal analysis. Thank you.